Hello y'all, we are Memphis Kim University and today we are doing another Calculus Done Wrong lesson where we wrong calculus before calculus can wrong us. And today is the day. Today is finally the day that we can talk about the Fundamental Theorem of Calculus, maybe mankind's third most important discovery behind the fire and the wheel. I'm a little bit biased, but let's get started. So let's talk about the Fundamental Theorem of Calculus. So fun that it's mental. So Fundamental Theorem of Calculus. How exciting. So what does the Fundamental Theorem of Calculus say? What is it used for? So keep in mind that in this video, we aren't going to prove the Fundamental Theorem of Calculus. That would probably be teaching calculus the right way. What we're going to do is we're going to skip that step and focus on the actual theorem itself and then how to apply it. So Fundamental Theorem of Calculus, what it says is that it allows us to evaluate integrals, definite integrals, f of x times dx equals f of b minus f of a. So this is what the theorem says, where little f and big F are related in a certain way. So let me just write out that relationship, where it says f prime of x is equal to little f of x. Or in other words, we're going to introduce new nomenclature here. If the derivative of big F is little f, we're going to reverse the relationship. What we're going to say is that the antiderivative of little f is big F. So we're just trying to introduce all the nomenclature at the beginning and then we'll explain it a little bit later. So antiderivative of little f is big F. So just think about this as maybe a parent-child relationship. So big F, let's talk about it with the derivative first. So little f is the child of big F. That means that the parent of little f is big F, sort of that one relationship. Same thing here. The derivative of big F is little f. That implies that the antiderivative of little f is big F. So this is the Fundamental Theorem of Calculus. We are going to practice it a bunch. If you want, pause your video, appreciate the beauty of the Fundamental Theorem of Calculus. So beautiful. And why is it so beautiful? It's because it allows us to find integrals without having to draw pictures, having to draw graphs. It would be very inconvenient if every single time we drew an integral, we would have to draw its graph and find its area. What this allows us to do is find integrals more easily without having to draw pictures. And I'm not going to complain because I'm not an artist. It's also kind of weird. We don't really care about the function itself. Actually, what we're doing is we're coming up with a new function that is tangentially related by derivatives and antiderivatives. And to integrate that function, you don't care about the little f. You come up with a new function called the antiderivative, and you don't care about any number in between a and b. You just evaluate the function at b, evaluate the function at a. And that's how you do it. So again, what we're going to do is we are going to take the antiderivative of the function, which is sort of thinking backwards. Which function's derivative is the one I'm starting off with? And then once we have that, we're going to plug in b and we're going to plug in a and subtract. Notice that the Fundamental Theorem of Calculus does have subtraction, subtraction, subtraction. So it's f of b minus f of a. The antiderivative of the function at b minus the antiderivative of the function at a. So before we start with examples, when I usually introduce the Fundamental Theorem of Calculus, I like to start practicing with antiderivatives because you need to be able to find antiderivatives to do this process. So let's try to talk about antiderivatives first. Whew. So I'm just going to make a table. Whenever you're thinking about antiderivatives, because we're so used to derivatives, oftentimes it's good just to think about derivatives backwards. So for example, let's say we have f prime of x and we want to have f of x. So we're starting off with the derivative and we want to come up with the antiderivative. So the first ones are going to be easy. Let's say cosine of x. So whose derivative is cosine of x? That's going to be sine x. Be careful with those negatives. So the relationship we know that we're very familiar with is that the derivative of sine of x is cosine of x. So using our new nomenclature, that means that the antiderivative of cosine x is sine x. So these are antiderivatives again. Let's keep going. What about the antiderivative of sine of x? Well, I know the derivative of cosine of x is negative sine of x, So whose function has derivative just sine of x? That's going to be negative cosine of x. So again, thinking backwards from derivatives isn't the worst thing in the world. Let's write out some derivatives that we might be familiar with. So instead of starting off with tangent and finding its derivative being secant squared, again, we're just moving backward. We're doing antiderivatives. So let's start off with secant squared instead. Whose antiderivative is secant squared? That's going to be tangent. So it's tangent x. Keep going. There's obviously more derivatives out there like secant tangent. Trying to think about that, thinking about derivatives backwards. Whose derivative is secant tangent? That's just secant. There's the annoying inverse trig ones as well. So for example, 1 over 1 plus x squared. What is the antiderivative of 1 over 1 plus x squared? Sorry, I can't talk. What we're trying to find is the function whose derivative is 1 over 1 plus x squared. So I know my derivative, that's going to be inverse then. Let's do one more in this sort of category. 1 over the square root of 1 minus x squared. This is going to be inverse side. So that's good to go. Now what we're going to introduce is we are going to introduce the power rule, because remember, when you're taking derivatives, the power rule is the most important thing. You take your exponent, you drop it to the front, and then you subtract 1. So for example, the derivative of x to the 7th is you drop that 7 down, so it's 7x, and then you subtract 1, so it's 7x to the 6th. So keeping going, we're going to add to our table here, f prime of x. F of x, so we have 7x to the 6th. It's going to be x to the 7. So what's the equivalent power rule? It's the reverse process of this. So instead of dropping the power, subtracting 1, what we're going to do is we are going to add 1 and then divide by our new exponent. So that's just the rule for the power rule. Maybe we can box it here. Let's say you have something x to the n. What the antiderivative of this is you add 1 to your new exponent. Or you add 1 to your old exponent to find your new exponent, and then once you have your new exponent, what you do is you multiply the reciprocal of that exponent, or flip the exponent in the front. So it's going to be 1 over n plus 1. So that's it. If you want, you can check yourself. If you bring the n plus 1 down, it will cancel out with n plus 1. It will subtract 1n. So the derivative of this guy is this. So let's just practice that real quick. So let's say we have x to the 10th. Well, if you have x to the 10th, what's the antiderivative of x to the 10th? We're going to use this power rule, so let's maybe draw some arrows to focus on it. So what we're going to do is we're going to add 1, so it's going to be x to the 11th. And then you just divide by your new exponent, or multiply by the reciprocal of your new exponent. That's the same thing. So what we're going to do is we're just going to divide. It's going to be 1 over 11. If you want, you can write this as x to the 11th over 11. Then let's just practice more. Just like with derivatives, a power rule is so great to use that we want to use it as much as possible. So anytime we have square roots, we're often changing things to be powers so that we can use the power rule. Same thing with negative exponents. So if you have square root of x, the first thing to do before you take the antiderivative will be to rewrite it as a fractional exponent. If you don't remember, square root of x is the same thing as x to the 1/2. And then finally, when you have x to the 1/2, let's do the power rule. So first off, focus on the exponent, add 1 to the exponent, so that's going to be x to the 3/2. 1 plus 1/2 is 3/2. And then again, at the very front, you multiply by the reciprocal. You flip that bad boy and you put it in the front. That's going to be 2/3. Let's keep practicing a few more and then we will be ready for practice examples. So let's do let's do 3, that's the worst 3 I've ever written. Let's do 3 over x to the 8th. So just like with the power rule, with derivatives, we're rewriting this as a negative exponent first. So this is going to be 3x to the negative 8th. That's the definition of negative exponents. Hopefully you can see this. If you can't, I'm just going to read it out. 3x to the negative 8. And then we're going to do the same rule. We're going to add 1 and then flip the new exponent. So it's going to be x to the what power? Well, we're going to add 1 to negative 8. Negative 8 plus 1, I believe, is negative 7. So it's going to be negative 7. Just keep this number in the front here, 3. It's not doing anything. And then what we're going to do is we're going to divide by negative 7. So we're going to divide by negative 7. And that's that antiderivative. Again, add 1, flip your new exponent. So the new exponent was negative 7. We divided by negative 7. Keep in mind that the power rule, this beautiful, beautiful rule, applies for every single exponent besides 1. That's why it's a little bit tricky. There's one that it doesn't apply to. That is x to the negative 1. So just be wary of this. You're going to see this antiderivative a lot of times, and sometimes maybe 5% of my students, they love the power rule so much that they also want to apply the power rule for this guy right here. But unfortunately, the power rule does not apply for this guy. This has its own special antiderivative. Think about derivatives and think about whose derivative is 1 over x. That's a famous function. That's ln of x. So that's ln of x. So we have that. So this rule, if you see in textbooks, they usually write n doesn't equal 1. You can only apply this rule when n doesn't equal 1. So that's that. We have a few more antiderivatives that we couldn't really fit in this table. Let me just erase the top of this guy because I think you have this written down if you are taking notes. So just a few more antiderivatives to talk about. What about e to the x? That's the best function of the rule because the derivative of e to the x is e to the x. So that's going to be e to the x. Keep in mind that just like with derivatives, you only do the power rule when x is the base, like x squared or square root of x, that's x to the 1/2. 1 over x to the 7th, that's x to the negative 7. So all of these are where x is the base. But there's a separate rule when x becomes the exponent. For example, 5 to the x. Remember that the derivative of 5 to the x does not use the power rule. It's 5 to the x times ln of 5. So same thing here. If you have a to the x, the derivative or the antiderivative won't be found using this. There's no add 1 and flipping business. What it is it's similar to this, but instead of multiplying by the ln of the number, you divide by the ln of the number. So it's a to the x over ln of a. So I'm going to erase this last few, and then we're going to about to start our examples. How exciting, how exciting, how exciting. So keep in mind that if you have two functions and they're added and subtracted, just like with derivatives, we're going to take the antiderivative of one, and then we're going to take the antiderivative of the other. Same thing with constants. If you have a constant in the front, sort of like with this 3, we sort of ignore it, just keep it in the front, and then we just take the antiderivative and multiply by 3. Like the derivative of 3 sine of x is equal to 3 cosine x, so that means the antiderivative of 3 cosine x is 3 sine of x. So sort of in terms here, using the same lingo, if you have the integral of f prime of x with a constant, we can call it, we'll write this, plus or minus g prime of x dx, and we have numbers in front of both of these things. Let's call them, I don't want to use a and b because I've already used a and b here. Let's just call them constant 1 and constant 2. So if you know these antiderivatives, again, you just take the antiderivative of f prime, so it'll be f of x, and then c1. Just put the constant in the front, plus or minus c2 g of x. And what we're going to do is we are going to evaluate this function right here. After we put the antiderivative separately, the plus or minus is splitting up, we're going to plug in b and a. And this might have been kind of confusing, but you'll see that we're just taking this for granted basically. And as we do the practice examples, it sort of comes naturally. One last thing before we talk about actually doing practice questions. Keep in mind that every function actually has an infinite number of antiderivatives. So if you take this guy right here, 7x to the 6, it is true that x to the 7th is the antiderivative of 7x to the 6, because the derivative of x to the 7th is 7x to the 6th. But if you add any constant, it still remains an antiderivative. For example, if you have 7x to the 6th, the antiderivative could be x to the 7th plus 3. Because when you take the derivative of x to the 7th, you'll get this. When you take the derivative of plus 3, you'll just get 0. So actually, 7x to the 6th has an infinite number of antiderivatives. It's x to the 7th, x to the 7 plus 1, x to the 7 plus pi, x to the 7 plus 17. all of these are antiderivatives. So if you look in a calculus textbook, and when I ask my students to memorize integrals, you're going to see a lot of these things called plus c's. So this is a way to write every single antiderivative, because it's not just x to the 7th, it's x to the 7th plus some constant. And what we're going to see in our next video is that oftentimes we're going to be solving for this plus c. So it is very important. The constant of integration is what it's called. It's not as important in this video because when you're evaluating definite integrals, which are integrals with numbers on them, you don't need to know that plus c because the plus c will cancel out once you evaluate the numbers, as we'll see. So that's just a small point. But the focus in this video is antiderivatives. Let's begin the show. Let's actually take some antiderivatives. So I'm going to erase this right here. Erase this, erase this, erase this. So my first question is going to be the integral. Let's see, what should we do? What should we do? Let's do -1 to 2 of x squared. Let's put a 6 in front. And then we're going to do minus 8x plus 2. So let's do this. So again, the very last things we talked about is just when we were listing our antiderivatives is to just take each antiderivative separately. Take the antiderivative of this, then take the antiderivative of this, then take the antiderivative of this. Also, these 6 and the 8 really doesn't matter. You just write them and then you take the antiderivative. So for 6x squared, this is our new power rule. So I'm going to explicitly say, let's write it out actually. Remember that the antiderivative of x to the n is you add 1 to your new exponent and then you flip it. So the antiderivative of x squared, that's going to be x cubed. That's the new exponent. We're adding 1 to our new exponent. Then we take our new exponent and divide by our new exponent. But there's already a 6 in the front of this guy, so 6 divided by 3 is going to be 2. So this is 2x cubed. Again, I added 1 to get a new exponent, which is 3, divided by that new exponent to get the constant in the front here. So let's practice again. So keep in mind that x is technically x to the 1. So what is our new exponent going to be? Well, it's going to be 1 plus 1, that's 2. So we can write that 2 down. So we form the new exponent, and now what we're going to do is divide by our new exponent. What's minus 8 divided by 2? That's minus 4. Now we have plus 2. We didn't talk about this, but technically we talked about it in the rule. It's x to the 0, because it's 2 times x to the 0. X to the 0 is 1. So what will be our new exponent? Well, it's just going to be x to the 1. And then when you divide by that, you're going to get just x. So this antiderivative is plus 2x. The antiderivative of 5 is 5x, because the derivative of 5x is 5. The antiderivative of minus 20x, minus 20 is minus 20x, because the derivative of minus 20x is minus 20. The antiderivative of pi is just pi x. So this is the first part of the Fundamental Theorem of Calculus. This is the first step. We took the antiderivative. We've been talking about antiderivatives a lot, but that's not what exactly what the Fundamental Theorem of Calculus says. What it says is you take the antiderivative and then you evaluate the antiderivative at 2, and then you subtract off and you evaluate the antiderivative at -1, which we'll do. Before we do that, remember that you can always check your work if you're sort of new to this process. If you take the derivative of this, you should get this back. So the derivative of 2x cubed, you drop to the front, that's 6, and then you subtract 1, so it's 6x squared, that is that. The derivative of this, drop the 2 to the front, that's minus 8, subtract 1 from the exponent, minus 8x. And then finally, the derivative of plus 2x is plus 2. So now we are ready for the second part of the Fundamental Theorem of Calculus, and this is really just the algebra step. So I'm going to put parentheses around all this. Sometimes people use vertical bar notation, and that's what I'm going to use throughout my videos. So it's kind of complicated looking, but it's not saying very much. All we're saying is that we're going to plug in this top number 2 into all of this, guys, and then we're going to plug in -1. Keep in mind that you always want to be very, very careful with parentheses, especially in this. So what we're going to do is we're going to plug in 2 first into 3 things, and then we're going to plug in -1, into three things, and we're going to just find what the answer is. The fundamental theorem of calculus does have a negative here. We can maybe put the fundamental theorem of calculus here because I love it so much. So the integral of some function is you take the antiderivative and you evaluate it at the endpoints. So we're going to plug in 2. Let's plug in 2. So this is the worst part of the fundamental theorem of calculus, actually adding things up. But 2 cubed is 8. 8 times 2 is 16. Now we have, I believe, another 16. So this is kind of convenient that it subtracts off. Because it's 2 squared 4. 4 times 4 is 16. Then we have a plus 4 at the end. 2 times 2. So again, I'm just plugging 2 into all of this. And then what I'm going to do is I'm going to plug in negative 1 into all of this. So keep in mind that negative 1 to an odd exponent is negative 1. Negative 1 to an even exponent is 1. So negative 1 to this cube is negative, so we have negative 2. Negative 1 cancels right here because it's squared, so we'll just have minus 4. And then when you plug in negative 1, it'll be minus 2 at the end. But keep in mind that there is this minus right here, and why is this minus so important? It came from the fundamental theorem of calculus. It's always f of b minus f of a. So now what we do is we just find these numbers. Looks like we have 4 in this parenthesis. And then within these parentheses, looks like we're going to have minus 8, I believe. So 4 minus 8. And then 4 minus 8, 4 minus 8, sorry, is 4 plus 8. That's 12. So this is our first fundamental theorem of calculus. Hopefully you're still ready to go after the weight or the greatness of this problem. But again, all we do is we take the antiderivative. In this case, we use the power rule a lot. Then you plug in the top number, you plug in the bottom number, and you just have fun. So let's practice another example. Maybe 3 more, because it is a pretty important notion. So let's do some with trig, because trig is the best, and by best I mean worst, but let's keep going. So we have 0 to pi. Let's do 2 cosine x minus sine of x dx. So here we're not going to be using the power rule, obviously. We're going to be using our trig rules and our derivatives for trig. So first off, the first thing to do is take the antiderivative. And when you're doing trig, you always want to think about derivatives backwards. The hardest part is probably negatives. So what's the antiderivative of cosine of x? Well, I'm thinking of my derivatives backwards. What's the derivative of sine of x? That's cosine. So the antiderivative of 2 cosine is 2 sine of x, because the derivative of this is this. So now, and then the 2 in the front is just the 2 in the front, because there's a 2 there. What's the antiderivative of minus sine of x? That's going to be cosine of x, because the derivative of cosine of x does include the negative. So again, negative is the hardest part about this. So it's going to be plus cosine x. We're going to wrap this around in parentheses, if I can write a plus correctly. And then we're going to plug in 0 and pi. So this is the fundamental theorem of calculus. This was the first step, taking the antiderivative. And now we're going to evaluate the antiderivative at the endpoints. So we're going to plug in pi here. 2 sine of pi plus cosine of pi. And then we're going to subtract. But notice again, I'm being very, very careful with parentheses because I'm scared that I'm going to miss the question. And then we're going to plug in 0 into all this stuff. So pi into all of this stuff minus 0 into all of this stuff. So what's sine of pi? Some of these are actually 0. If you don't know, sine of pi is 0 because you're on the unit circle, and pi deals with the point -1, 0. Sine is the y-coordinate, so sine of pi is 0. Same thing with sine of 0. So what's cosine of pi? Cosine of pi is -1. Again, pi goes with -1, 0 on the unit circle, and cosine is the x value. What's cosine of 0? Well, that point is 1, 0, goes with the x value, so just 1 minus 1 minus 1 is minus 2. And that's it. So that's another example of the fundamental theorem of calculus. Again, just take antiderivatives, plug in the top thing, plug in the bottom thing, and you're good to go. Let's do a few more. Let's erase the fundamental. I think we know it by now. Let's do integral of 3e to the x from 0 to, let's say, 4. and then we'll do a minus square root of x plus 2. So if you want, you can pause your video. I'm going to answer this question in 3 seconds. Too excited to sort of contain my excitement. So let's try to practice this for 3 seconds. I don't even know what I'm saying anymore, blah, 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 blah. And then in 3 seconds, it's already been like 20 seconds, but let's just do the question. So 3, 2, 1, let's go. So the antiderivative of 3 e to the x, I love to see e to the x because the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. So we have 3 e to the x. This one, again, is going to be the power rule. The power rule is the best rule, but in order to use the power rule, oftentimes it's good to change it to a power. So on the side, I'm going to write it as x to the 1/2. So it's going to be minus x to the 3/2, because again, you add 1 to your exponent. 1/2 plus 1 is 1/2 plus 2/2, that's 3/2. Then don't forget, take your new exponent and flip it and put it in the front, 2/3. Then the antiderivative of plus 2 is plus 2x, because the antiderivative of any constant is constant times x, like 7 is 7x. So it's plus 2x. So now we've done all the calculus. All we have to do is do a few algebra steps. We're going to plug in 4 and 0. So some of this will be easier and some of this will be harder. So when you plug in 4, it will be 3 e to the 4th. Can't really simplify that, so we'll leave it like that. Then we have 2/3 times 4 to the 3/2. You might not know 4 to the 3/2, but remember that if you're ever finding a number and going to a fractional exponent, it's oftentimes good to do the denominator if possible, because then you'll get a smaller number. So on the side here, 4 to the 3/2, well, it's the same thing as 4 to the 1/2 cubed, so that's going to be 2 cubed, which is 8. So again, just take the fractional exponent first, and then do the numerator. Do the denominator first, then the numerator. The denominator, it's hard to say that word a lot of times, but the denominator is the root, and then the numerator is the power. So in this case, we get 8, but we still have this 2/3, which came from the Fundamental Theorem of Calculus, from antiderivatives. So it's going to be 2/3 times 8 after we plug in 4. So I believe it's minus 16/3. Finally, we're going to have 4 times 2. That's pretty easy. That's plus 8. Next, we are going to not forget about 0. We are going to plug in 0. When you plug in 0 here, you get 3 e to the 0. But anything to the 0 is 1, so you're just going to get 3. 3 times 1. We could do the same trick with fractional exponents, but 0 is a better number. 0 to the 3/2 is 0. And same thing with 2 times 0 is 0. 0 is a great number. So it's going to be minus 0 plus 0. So it looks like we have 3 e to the 4th. We have minus 16/3. I just want to combine all the numbers together. Again, this is the least important step. More important is just being able to find antiderivatives, but we might as well try to simplify as best as possible. 8 is 24/3. And then 3 is minus 9/3. Let's see if I can do math. So 16 minus 16 minus 9 is negative 25. So it looks like we just have 24 minus 25. In the end, this is going to be 3 e to the 4th minus 1/3. So same sort of steps. We took the antiderivative using the power rule when necessary, and we sort of plugged in the top number. Was careful about that. Negative, because the Fundamental Theorem of Calculus is negative. And then we plugged in the bottom number into the antiderivative as well, and simplified, being careful with parentheses, of course. So one last question, and then we should be good to go. So I'm going to erase this guy. Let's do integral of, what should we do? What should we do? What should we do? Let's do 1 to 2, 3 over x squared minus 4 over x. So last one, again, if you want, pause your video. I feel like we're getting better and better at this, so if you want to sort of see what you're made of, I'm going to do this question in 3, 2, 1. Let's see what you got. So again, what we're going to be doing as much as possible is to employ the power rule. So for this first guy right here, I'm going to rewrite it. Remember that if a x to an exponent is in the denominator of a fraction, sorry, I sort of lost my train of thought there, that becomes a negative exponent. So we can rewrite this as 3x to the minus 2. So let's try this guy right here. Let's try to take the antiderivative. So what we're going to do is we are going to add 1 to your old exponent to form the new exponent. Minus 2 plus 1, I believe, is minus 1. Then we are going to divide by our new exponent, because it's always add 1 to the new exponent and then divide by it, or flip it is another way to say it. But 3 divided by negative 1 is the same thing as 3 times negative 1, it's just minus 3. Minus 3 here. Looks like we have the right thing, because if you took the derivative of this, the negative 1 would drop down. It would be negative 3 times negative 1, which is 3. We would subtract 1 from our new exponent, so it would be minus 2. You could do the same sort of thing for this guy right here, but just don't be tricked. This is sort of a trap. Remember that you cannot employ the power rule for this guy particularly, because if you rewrote this, this is 4x to the negative 1. And again, the power rule does not apply for one single number, one single exponent, and that is this one precisely, that's negative 1, because this antiderivative is famous. You're going to see it a lot, just like when you take the derivative of this function. This is just ln of x. So it's 4 ln of x. And then what we're going to do is evaluate it at 2 and 1. So I like my vertical bar notation. X is equal to 1 and 2. Keep in mind that just like with derivatives, with integrals, if you're using the power rule, you change things to negative exponents or fractional exponents in order to do the power rule. But once you need to plug in a number, it's oftentimes good to change it back. So in this case, I'm going to rewrite this as a fraction. So it's going to be minus 3 over x minus 4 ln of x. Let's see if I can squeeze it in. It's still going from 1 to 2. So if you can't read that, let's just try to verbally do it right now. So when we plug in 2, it looks like we're going to get minus 3 halves. We can write some equal signs. When you plug in 2 here, that'll be ln of 2. Not a number that you need to know or need to simplify. So it's 4 ln of 2. We're going to subtract, and now we're going to plug in 1. So when you plug in 1, it's going to be a little bit easier because it's negative 3 over 1, that's just negative 3. And then ln of 1 is an ln that you should know because e to the 0 is 1. That means ln of 1 is 0. That's where it crosses the x-axis. So it's minus 0. It looks like we're good to go. Minus 3 halves. Just be careful with these negatives. This negative came from the evaluation of 1. This negative came from our new friend, the Fundamental Theorem of Calculus. So it's negative 3 halves plus 3. When you're simplifying this, that's going to just be 3 halves. And then finally, it's minus 4 ln of 2. And you can simplify this with log rules if you want, but I'm just going to leave it like this. So that's the Fundamental Theorem of Calculus. Hopefully this has allowed you to learn how to evaluate integrals. You're going to be doing this so much, just like you took a lot of derivatives in the first half of calculus, you're going to be evaluating a lot of integrals. And unfortunately, it is going to get harder when you're evaluating integrals. We're going to be doing things in the future, way future, like use substitutions, integration by parts, integrate partial fractions, and things like that, if you're taking BC, for example. So it's really important, and it's just so beautiful to really master the Fundamental Theorem of Calculus. One way to do that is to watch our Girls Teach Calculus video. That video is in the description below this video, and one of my former students, probably explaining things way better than I do, she goes through quite a few examples, maybe like 12 or 14 or so, where she practices antiderivatives, she practices the power rule, she does trig functions and inverse trig functions and things like that. So be on the lookout for that if you need more practice. But thanks again for watching. In our next video, we are going to be using the Fundamental Theorem of Calculus to find the antiderivative formula for the antiderivative, or finding the antiderivative at a point. I know you're very excited, but be on the lookout for that. And I hope I will see you in that video. Thanks again for watching.